So this is today's Researcher's Desk session, where we will hear Paul Glantz from Stockholm University. And I'm very happy that we can hear from your research about the humidity paradox of climate change. And Paul will share his presentation in a second. And yes, you're welcome to ask questions then also after the presentation. And I'm also particularly looking forward to this because I used to see Paul more often also in the Researcher's Desk board. And so he has several heads on. And yes, for those who don't know me, my name is Romina Martin. I'm also working at the Stockholm University within the Stockholm Resilience Center. And I'm happily complimenting Alistair Skelton today, who is still in the field study. So with those few words, I'm looking forward to hear and learn more from you, Paul. You're welcome to share your presentation, and everybody else is welcome to collect questions for later. Up to you, Paul.
Thank you, Romina. Here we have it. So very welcome. So the title, as Romina mentioned, is associated with the humidity paradox. So the role of the humidity paradox of climate change for recent warming trends. So this study at the moment is in preparation, and you see my co-authors here on the left that very much contribute to this work is Kevin Noon and Fredrik Schenk, as you see here on the left. And so I will give an introduction of the warming that are occurring, and particularly when we focus on the latest year, because the warming is very rapid. And so in this study, we try to explore possible reasons for the warming, and we believe very much for that one part of this thing that are explaining the warming is this humidity paradox that I will coming back to. So I will give you a brief description of the background of the warming, and I will start to take you back approximately 2.5 years to the latest IPCC report. And here you see the results of the temperature increase that we have at the current period. And the reference period you see here is when we're going back to 1850. We take an average according to 1850 up to 1900 then. So this is the anomaly for the temperature in the lowest part of the atmosphere. And it's subdivided according to warming over land and ocean, as you see here. And comparing the latest full decades, 2010, as you see here. So the warming over land is about 1.6 compared to the ocean 0.9 then. And in some way, it's not surprising because we know when we are warming up the planet, much of the heat is distributed in the column of water in the ocean then. So we have a delay in the warming from the oceans. And that means even if the emissions of the greenhouse gases will start to decrease, we will still have an effect of the warming from the ocean, approximately up to hundreds of years then. But on the other hand, it surprised me for sure that we see that the difference is so large when we're comparing the warming over land compared to the oceans. Since when we go back 11 years to the previous IPCC report, we can take a look in the curve. Let me see, you see my pointer here. We can go back here and the difference was not so large. So we didn't thought about that what should happen during later period as you see here. So this is very much related to humidity paradox. But first, I will also mention that at the same time as the IPCC report was launched, the latest one, 2.5 years, we were also involved in our own study to investigate the warming over Europe. And also when considering the warming over Europe, what we see here, when we are comparing the summer half year, we have taken average of April, September, and we're comparing the latest full decade with the 80s. So we deal with a period of 4 decades then. And the data I should mention here is from ECMWF Era 5 reanalysis. And ECMWF stands for European Center for Medium Range Weather Forecast. And so a reanalysis is combining observations from space based on satellites. So it's based on satellite observations and ground-based measurement in combination with modeling simulations. And so I have subdivided here according on the left for clear sky conditions and all sky conditions. And when we're comparing these 2 decades, we also see the similar things, that the warming is very rapid, the warming is very fast over land. And this is in line with Copernicus, the European Union's climate service, that confirmed that Europe, among the continents, the fastest warming is actually occurring where we're living in Europe then. And then we the last year, when the warming start to increase even faster, I will say. So the left figure you see here in the top is a summary of the warming when we're comparing the latest year, 2023, but also the 4 months of this year with and we also have all the decades, as you see here, back to 1940s. And all these results that we have for these decades and the previous year, we have used the reference period, as you see in the right bottom here, a 30-year period from 1981 to 2010 then. And then we can confirm that the latest 11 months is on the record when you're comparing with previous year. And we see also that September 2023 sticks out, which is also shown in this figure in the left. And it sticks out even more when we take a look at the warming over land. So in the left bottom figure, I've taken average according, for the warming over land, as you see here. So this is relevant when we start to think about the humidity paradox. And if you just also sum up the warming for September 2023, this figure on the right here also indicate compared to the ocean then. I've also marked out El Niño event, that we have this natural weather phenomena that also pushing up the temperature somewhat, that we should also keep in mind. Finally, for the background on the warming, because we could also take a look at the anomalies. This is for annual temperature anomalies, including the last year, 2023, which you see in these figures. And here we have comparing the annual values with the reference period, as you see in this figure, 1850 to 1900, take an average according to that. And we have Copernicus, and we have also time series from California research team, and also from the Met Office in UK. And the striking here is actually when we take a look at the very rapid warming that are occurring at present, that we are very close to the climate benchmark of 1.5 degrees, which is related to the Paris Agreement, then, which you know about. Okay, we try now to analyze data and try to explain the reasons for this very rapid warming that are occurring. We don't have the full explanation, I would say. Much of the discussion, what we have heard about, is that the warming is going very, very fast over the oceans. And this surprised everyone, I would say, among the scientists. And it's very relevant to talk about this, actually. But not much talk about the rapid warming over land. And that I will focus very much on now. But I will also introduce a little bit about the radiation balance that we have in the lower atmosphere. Try to explain a little bit what is the important factor to describing the balance, and also the reasons why we have a natural greenhouse effect that lead us to a planet that we can live on, actually. So how is the mechanism to warming up the lower part of the atmosphere? So here you first see incoming solar radiation. But of course, some of this solar radiation is also reflected back to space at the surface. We could think about snow and ice covered surface that have a really efficient reflection of the solar radiations. Is included in the we can name it as the albedo effect. But the important thing also that we also have the cloud that are including in the planetary albedo. So white clouds, as we see them from above, is very efficient to reflect solar radiation. So on average of the planet, so 30% of the solar radiation is not used for warming up the planet. So this planetary albedo is a very important number to keep the radiation balance on the planet. So the risk is then at the present day that we are disturbing this, actually. So this is one component of the radiation balance that we need to take in consideration. But of course, we have the greenhouse effect, which I touch on. And so the greenhouse gases means that much of the infrared radiation is emitted back to space. On average for the planet, meaning that we have a planet that we can live on, as I mentioned, approximately 30 degrees higher temperature, thanks to the natural greenhouse effect. The third part that we have to deal with when we think about how the planet or the atmosphere is warmed up, and it's particularly the lower part of the atmosphere we talk about when we take a look at the global warming. So all this energy that are reaching the ground, or some of it, I should say then, is converted to heat flux. And heat flux, you can separate it according to the left, sensible heat flux and latent heat flux. So latent heat flux, if I start with that, is evaporation of water vapor. So latent heat flux is hold in the water vapor. And when the water vapor are converted, forming the clouds, then the heat is released then. Sensible heat flux, you can briefly think about it. When you're warming up the ground in turn is warming up the lower atmosphere. So if we focus a little bit on the heat flux, because if we go back to our previous studies, we saw actually when we took a look at the Southern Europe, including France, that we have a shift in the heat flux. So when we take a look at the latent heat flux here on the left, and it's the same period that we compare with, the latest full decades with the 80s. And we see actually a decrease in the latent heat. This means that we have a decrease in the water that we have in this region in Southern Europe. And so the question arises, where is this energy that are coming from the solar radiation? What is it doing? Where is it popping up? Because if you are drying out the Southern Europe, which is indicated in the left figure, then the energy is converted more to sensible heat flux. And that means an extra warming of the lower atmosphere. And you can see it as a positive feedback due to the enhanced man-made greenhouse effect due to the global warming. So the feedback, the positive feedback, it goes in the same direction as the original warming of the enhanced greenhouse effect. So we get an extra warming because of that then. It's actually another effect of this when you see that more of the energy is popping up in the sensible heat flux. Because when you are reducing latent heat flux in the left figure, you also get the reduced evaporative cooling. So in a natural balance that you have for the planet, when it's not disturbed, you actually have a natural reduced cooling effect from what is named with reduced evaporative cooling. So in this evaporation from the surface, you also get a cooling effect in a natural situations. But since we're drying out the surface, you are reducing this evaporative cooling. So it's very important in combination with the humidity paradox that I will start to talk about next, is also to realize what happened in the surface of the planet over land that we focus on here. I will also sum up this later on, but I will now jump into the humidity paradox. And so in this figure, we take a look at the relative humidity, and the relative humidity describe how close we are saturation of the water vapor. And 100% in relative humidity, then we are at the saturation point, which means that the water vapor are converted to cloud droplet or forming the clouds then. And then we can also compare it with the water vapor that we have here in the blue curve. And you have these values on the right axis for the water vapor. The relative values is on the left axis. We see an anomalies according to this. And the reference period you also see here, it's a 30-year period once again here. So this is for the September month. We see an average according to that. So in the same time as we actually have more of water vapor also over land, it's not strange in a way, because when we are warming up the planet, we get more of evaporation from the ocean. And this water vapor, of course, is also transported over the land. Otherwise, we couldn't have any rain, for example, over land. So much of the water vapor and water is coming from evaporation over from the ocean. But at the same time, we see that the relative humidity is decreasing. So this is a little bit the paradox, since if we are thinking it over land that we should have more water vapor, in the first thought of it, we should think that, okay, it should favor cloud formation. But the thing is that we see that the relative humidity is decreasing, so it goes in the opposite direction. And the reasons that we believe on is, even if we have more of evaporation of water vapor over the ocean at present, it's not enough. It don't keep pace with the very rapid warming that we have over land. So, so the saturation process is very much dependent on the temperature is the only meteorology parameter is depending on, but actually the amount of water vapor you have. So the amount of water vapor goes in the direction it should be suitable for reaching higher relative humidity. But the thing is that we're warming up the land so much faster that the relative humidity actually is decreasing. And this is also shown that we take an annual mean for this period back to approximately 4 decades time. So, but in this case, the increase in the amount of water vapor is not so strong as compared when we take a look at September, as you see here. So the strongest changes that we have is actually in the relative humidity, and therefore we can take a look at this figure, which shows the changes in the relative humidity when we're comparing the latest approximately four decades. So on the left, it's an average according to September, and on the right is according to annual mean, as you see here. And the changes here is in percent per decade. And we see more or less over land at more or less all places that we have a decrease in the relative humidity, with exception for part of Asia, as you see here, the South Asia continent, India, as you see here. And one reason for that is likely, at least a part explanation of it, that we have a positive relative humidity trend over India is because of all these aerosol particles that are masking incoming solar radiation at present time. So this is the relative humidity, but an important change in this data that we have here then is that, yeah, I should mention, one effect of the increase in the relative humidity is that we are at present day in the situation that we have a decrease in the clouds over land on average, I would say. And this will also reflect the changes in the incoming solar radiation. So the most accurate parameter to take a look at that, the decrease in the clouds, is actually to take a look at the incoming solar radiation. You remember my planetary albedo short description of it, because the clouds is very important in the planetary albedo. And the effect then on reduction in the clouds, mainly in the clouds, I would say, is that we get more of incoming solar radiation, which is reflected at the top of the atmosphere. But I could also show a similar figure for the lower atmosphere, and we see the same trend as you see in this figure. So all these positive anomalies denoted with the red colors over land here, over ocean also, means that more of solar radiation has reached the lower part of the atmosphere, and also the ground is available to warm up the lower part of the atmosphere. Is available, extra available for the radiation balance that I described for you. And if you see this for September 2023, when we take an average on the left figure over land globally, we see also that the latest year is the year for September 2023 that sticks out the most, I would say. So finally, we can also take a look at the infrared radiation, because, no, I should also mention these two areas here. So this is a little bit exception for the positive anomalies, because here we also have more of the polluted air at present day, all these aerosol particles impacting the incoming solar radiation, both considering the cloud properties, but also in the cloud atmosphere. So on average, we see that the aerosol particles marked with this black circles here are masking incoming solar radiation in a way. So we can also take a look at the trend in the infrared radiation. So now we jump over to greenhouse effect, the greenhouse gases, because you have to think about if we're reducing the planetary albedo, we get more of solar radiation into the system at the surface. And of course, this will also increasing more of infrared radiation. It will increase the greenhouse effect, actually. And when we take a look at, in this case, at the surface level, the infrared radiation in the direction to the ground, we see very strongly positive feedbacks over land and ocean. And for the ocean on the left, we see an average of it globally, very strong, where September 2023 sticks out the most then. We have also comparing, this is the final figure I will show for you. We have also comparing the ERA5 reanalysis with real series observation. And this series observation is satellite observations. So this is a validation of the ERA5 reanalysis product. And it's for the period where we have data from Sirius 20.1 to 2023, approximately 2 decades then. And when we're comparing here for the normalized root mean square deviations, it's a direct comparing of the values. We see very low percent values, around 5, lower than 10, with exception for the area over the oceans close to the South Pole. But for an average over land, when you're comparing the two different products, we have quite good agreement, I will say, between ERA5 and Sirius, with this shown in the right figure here then. So if I sum up this presentation, and one question we can I could expose for you then is, why are clouds decreasing over land at present? I will point to 2 things that I mentioned for you. We have reduced evaporation from land, and the second is connected to the humidity paradox. We get the faster warming over land than for the ocean surface. And this also means add to this reduction in the relative humidity. So both these 2 changes is influencing and affecting the relative humidity in a way that is decreasing. And this means then that we are further away from saturation of the air. We could also think about the humidity paradox in another way, which means that, think about it, the water vapor, instead of being there, and at present at some region we have more of it also. So instead of forming the clouds as this had done, if we're going back in time, we get more of water vapor over land. And in addition to the anthropogenic greenhouse gases, this likely contributing to an even stronger greenhouse effect. And that's actually we see for September 2023, when we see so strong increase in the infrared radiation in the direction to the ground. So that's a really strong indication of an enhanced greenhouse effect. So if I just repeat the positive feedbacks that we have based on ERA5 and Sirius satellite observations, so we get a decline in the clouds, indirectly shown by that we get more of solar radiation coming in to the ground. But we also have an increase in a decrease, sorry, in the surface albedo. I didn't show you that, but we see that for the particular winter month, that the snow cover seasons, for example, in Central Europe and Eastern Europe, that the period of snow is shorter at present. And this means that we have an increase in top of the atmosphere and surface net solar radiation. This means in turn that we get an increase in surface infrared radiation in the direction to the ground. And finally, all this together means that we get a stronger warming effect by that. I should also mention the aerosol particles, the temporarily and short-lived aerosol particles that temporarily is masking incoming solar radiation, is masking the greenhouse warming. And so this effect you can see from Europe and Eastern US, that we have much cleaner situation today. So we can see this effect is a bit gone. It don't as appear. So what has happened that over Europe and Eastern Europe, or full Europe, is that we have an exposure of the man-made greenhouse warming. But we have this masking effect over other regions of the Earth, as I touched on, for example, over Southern Asia and also Eastern Asia then. Okay, thank you. And I stop here and ready for questions.
Yes, this time we need, thank you so much, Paul, for presenting.